Today, we're going to dive into one of the biggest, most mind-bending problems in all of physics. You see, we have this deep, nagging conflict between our two best theories of the universe. One describes the really big stuff, planets, galaxies, the whole cosmic dance. And the other describes the really small, atoms, particles. They both work beautifully on their own turf. But when you try to make them work together, well, that's when the laws of physics just seem to break. So how do we fix this? Let's get into it.
The search for the universe's rulebook is nothing new. For centuries, people like Giordano Bruno have looked up at the stars and tried to figure out the fundamental laws that make everything tick. And that journey has led us to some absolutely incredible places. But it's also brought us to this huge crossroads, a kind of deep crack running right through the foundation of physics.
So here's our game plan. First, we'll meet the two pillars of modern physics. Then, we'll zoom in on exactly why they just can't seem to get along. We'll look at the decades-long hunt for a solution, and then, and this is the really cool part, we'll explore a wild new idea that just flips the whole problem on its head and asks what that all means for the very fabric of reality itself. Okay, so to really get a handle on the problem, we first need to introduce the two main players in this story. And these are, without a doubt, the two most successful scientific theories humans have ever come up with: general relativity and quantum mechanics. So on one hand, you've got general relativity. This is Einstein's masterpiece. It paints this beautiful picture of gravity, where spacetime is a smooth, continuous fabric that gets curved and warped by massive objects. It works on the grand scale, think stars, galaxies, and it's deterministic. You tell it how things are now, and it'll tell you exactly how they'll be later. But then you have quantum mechanics. This is the rulebook for the tiny, microscopic world. And down there, reality is, well, it's grainy. Energy comes in these little distinct packets called quanta, and everything runs on probability. You can never know exactly where a particle is, only where it's likely to be.
Now, for most of what physicists do, this split is totally fine. You use one set of rules for a planet and a completely different set for an electron. But what happens when you run into something that is both incredibly massive and incredibly small? I'm talking about the singularity at the center of a black hole or the very first moments of the Big Bang. In those extreme cases, both rulebooks have to apply to the same thing, and they violently disagree.
And the scene of the crime, the exact place where this fight becomes impossible to ignore, is right here. This is Einstein's famous field equation. It's this elegant bit of math that's basically the engine of the universe, telling spacetime how to curve and telling matter how to move through it.
So here's the key part. The left side of this equation, that g mu nu, that represents the geometry of spacetime itself. It's the smooth, continuous, well-behaved fabric that Einstein imagined. This is the classical world. It's definite.
But then you look at the right side of the equation, that T mu, that represents all the stuff in the universe, all the matter and energy that's doing the curving. And here's the thing, we know from a century of experiments that all of that stuff is fundamentally quantum. It's fuzzy, it's probabilistic, it can be in multiple states at the same time.
And this shows you the problem perfectly. To be really accurate, physicists like Jonathan Oppenheim point out that we have to put a little hat symbol over that T, which turns it into what's called a quantum operator. That basically means it's not a single number, it's a whole set of quantum possibilities. So now look at the equation. You're saying a smooth, definite classical thing on the left is somehow equal to a fuzzy, probabilistic quantum thing on the right. That just doesn't compute. It's like saying a finished painting is equal to the possibility of a painting. It's a non-starter.
So, what do you do? How do you solve this? Well, for the better part of 100 years, the mainstream approach has been driven by one single, really powerful assumption about which side of that equation needs to be fixed.
Right. The overwhelming consensus has always been that gravity is the one that has to give. The thinking basically goes like this. Since we know for a fact that matter is quantum, then the thing it interacts with, spacetime itself, must also be quantum deep down. So the goal for decades has been to quantize gravity, to figure out how to put a quantum hat on the left side of the equation so that it matches the right.
And this quest has led to some of the most complex and fascinating ideas in all of science. You probably heard of some of them, like string theory, which says everything is made of tiny vibrating strings, or loop quantum gravity, which imagines space-time is woven from these tiny, discrete loops. I mean, these are brilliant, truly profound theories, but they all have the same problem. After all this time, we still have no way to actually test them to see if they're right.
But what if that basic assumption, that gravity has to be quantum,
What if that's just wrong? A pretty new theory is proposing a completely different way out of this mess, a path that hardly anyone was even thinking about. And it all starts with this simple but really provocative question from physicist Jonathan Oppenheim. Do we really have to quantize gravity? What if, instead of trying to cram gravity into the quantum world, we could find a way for the classical and the quantum to just consistently exist together?
This new idea is called the post-quantum theory of classical gravity, and it's not some halfway measure. It's a real, mathematically consistent theory that allows for a smooth, classical spacetime to interact directly with all that fuzzy quantum matter. The whole point isn't to force one side to become like the other. It's about building a stable bridge that lets them talk to each other.
Now here's where the whole thing just flips the old approach upside down. It starts by assuming gravity is classical, full stop. And instead of changing gravity, it's actually quantum mechanics that gets a tiny little tweak. And the secret ingredient, the thing that makes it all work, is that the interaction between the two is fundamentally stochastic, which is just a fancy word for being inherently random and unpredictable. This built-in randomness is the key that lets the theory sidestep all the old arguments that said a hybrid theory like this was just flat-out impossible.
Okay, so let's say this wild theory is right. What would that actually mean for the universe we live in? Well, the consequences are pretty huge, and they might even solve a few other deep mysteries while they're at it.
At the very core of this theory is a fascinating idea. The smooth fabric of spacetime isn't perfectly calm. Because it's constantly interacting with quantum matter, it picks up a tiny bit of intrinsic unpredictability. You can think of it like a tiny random wobble or jitter that's always there, affecting everything that exists within it.
So, how does this little random wobble actually change anything? Well, it has a massive impact on one of the weirdest parts of quantum mechanics, superposition. That's the idea that a particle can be in many different states or places all at once. According to this new theory, that super delicate quantum state just can't last when it's being constantly nudged by spacetime's random wobble. The wobble eventually breaks the superposition, forcing the particle to decohere or collapse into just one single definite state.
And this is a huge deal. For 100 years, quantum mechanics has been haunted by this thing called the measurement problem. Basically, why does a quantum system only snap out of superposition and into a single reality when we measure it? This theory offers a beautiful answer. The collapse isn't caused by us, the observers. It's just a natural, ongoing process caused by the fundamental, random interaction with space-time itself.
So all of this leaves us standing at a really interesting fork in the road. We have two completely different pictures of our universe. Both are trying to solve the same deep problem, but they point to two very, very different kinds of reality.
So here's the choice we're facing. The traditional path, quantizing gravity, says that if you could zoom in far, far enough, you'd see that space-time is grainy. It's made of tiny, discrete quantum bits, just like everything else. But this new post-quantum path says no. Space-time is smooth and continuous all the way down. But, and it's a big but, its interaction with matter introduces a fundamental, unavoidable randomness into the whole system.
Which leads us to the ultimate question, doesn't it? What is the true nature of space-time? Is reality at its core a pixelated, grainy image? Or is it a perfectly smooth canvas that just has an inherent, unpredictable wobble to it? Right now, we just don't know the answer. But the very fact that we now have a brand new, legitimate path to explore makes this one of the most exciting times ever in fundamental physics.